Forecasters who have been exposed to wind profiler data have found them to be reliable and very useful in nowcasting and short-range forecasting. The last two videos in this series deal with forecasting applications of profiler data. This video describes what happens to the data before they reach the workstation, in particular, the subject of quality control. It's important to become acquainted with the potential problems in profiler data and with methods of automatic detection. In fact, the more you know about the collection and processing of the data, the better you can interpret them. Data problems fall into three categories: measurement uncertainty, unrepresentative observations, and spurious measurements. Measurement uncertainty is associated with the statistical randomness inherent in every measurement. Assuming that the instrument provides unbiased measurements, that is, no systematic error, the method of sampling and the precision of the instrument determine the size of the random error. For a well-designed instrument, this random error is small and is distributed about the correct value in a bell-shaped curve. If the true value is represented by this line, then systems with small random errors will have a narrow bell curve. Those with larger random errors, a broader bell. The horizontal winds reported by the profiler have a random measurement error of about 1 meter per second, a couple of knots. Analysis techniques that use many different observing systems, each with different characteristics, take the random errors into account. Thus, there is no need for concern about random errors in the wind profiling system. They are small and tend to average out to 0. Unrepresentative observations accurately describe the state of the atmosphere at the sampling point, but do not represent conditions on the scale of the station's separation. An example is a surface temperature measured in the outflow of a thundershower. Likewise, a profiler may measure the winds inside a thundershower, but those winds may not be representative of the synoptic or mesoscale winds in the area. Here is a time height cross-section showing some winds measured during a thunderstorm. At this hour, the winds show a shift to the south. Then, in the next few hours, the wind direction is different from that before the storm, but consistent for several hours. During the hour of the thunderstorm, the winds between 7 and 10 kilometers are clearly not representative of the flow before or after. In fact, as we will explain later, there is a chance that these thunderstorm winds, though quite consistent within the hour, are taken in such disturbed conditions that they are not valid. Some winds, apparently thunderstorm contaminated, did not have such vertical consistency and were discarded. The final problem is spurious measurements. They occur when the instrument malfunctions or when one of the operating assumptions is violated. It is desirable to remove these errors before plotting the data. It is necessary to remove them before any application program uses the data. This video focuses on the causes of spurious measurements and the methods of detection. The first video described phenomena that can adversely affect the operation of the profiler. We will review the most important of these and illustrate, where possible, their appearance in the final data. As shown in the manual, the profiler beam does not radiate all its energy in a narrow, cone-shaped beam originating at the antenna. Due to the finite size of the antenna, the beam cannot be focused into a narrow cone. Small amounts of energy in the beam leak outside the ideal cone and propagate in other directions, These are called side lobes. Under normal conditions, the energy returned from a side lobe is so much smaller than that from the primary beam that it has no effect on the velocity measurement. However, the reflectivity of clear air is weak, and side lobe returns can overwhelm the main beam returns if the side lobe strikes a highly reflective object, such as a rain shaft, as shown in the first training video, or even a ground target like a building, tree, or truck. Tropospheric bending, which occurs in very stable air masses, can increase the chance of seeing a ground target. This effect is the same as that which creates false echoes on a conventional weather radar. This means that the chances of seeing ground targets in the profiler data are greatest in stable conditions, behind a cold front or under a strong nocturnal inversion. There is a ground clutter algorithm built into the velocity processing system which removes the effect of ground targets having zero velocity. Moving targets, however, can create a problem. In the demonstration network, the profilers are located far from cities. That should help minimize the chances of side lobe trouble. An important assumption in the wind profiler measurement is that the winds are uniform over the area covered by the three profiler beams. The beams are separated by a distance of about 1/4 the height above the ground. For example, at 8 kilometers, the beams are separated by 2 kilometers. The network profilers receive reflected power from raindrops as well as turbulent eddies in clear air. So they measure the fall velocity of precipitation as well as the wind velocity. The fall velocities can be accounted for in the retrieval of the horizontal winds from the radial velocities, but the fall velocity must be uniform in each of the three beams. In stratiform precipitation, the radar should perform flawlessly. The type of precipitation that can cause trouble is convective, when there are strong rainfall gradients. If one of the beams samples the precipitation and the others do not, or if the fall velocity of the precipitation varies from beam to beam, then the calculation of horizontal wind will be meaningless. The manual demonstrates this with a concrete example. This is one error that has a clear signature in the data. Because of the way the data are averaged, more on this later, the most common situation is to have precipitation contributing to the radial velocity average in the off-vertical beams, while the vertical velocity average is set to 0 in the vertical beam. In this case, the precipitation appears as a relatively strong wind from a direction halfway between the pointing directions of the off-vertical beams. For example, if the beams point north and east, the precipitation-contaminated winds will be from the northeast. If the beams point northeast and southeast, the erroneous winds will be from the east. This is an example from a profiler having beams pointing north and east. Note the strong northeast winds here. The surface observations at this time indicate rain showers. Precipitation contamination is more likely to show up at low levels because there the precipitation is liquid and large enough to have a substantial fall speed. Drizzle and cloud droplets, which have a fall velocity less than the radial velocity measurement error, about 1/5 of a meter per second, are not of concern. As you can tell from this case and the hypothetical case presented in the manual, the errors from precipitation contamination are typically quite large. This is, in fact, beneficial. The errors can easily be detected by the quality control algorithms that look for inconsistency in the reported winds from one level to the next. The profiler's operating frequency and sampling interval limits the maximum radial velocity that can be measured unambiguously. The maximum radial velocity is known as the Nyquist velocity, or the unambiguous velocity. As soon as the radial component exceeds the Nyquist velocity, it will appear to change sign. The effect can be illustrated with this speedometer that reads from 0 to plus 30 knots and 0 to minus 30 knots. The Nyquist velocity for the radial velocities in the low mode of the profiler, below 9.25 kilometers, is about 30 knots. When the radial velocity is below the Nyquist velocity, for example, when it is 25 knots, speed is read correctly. However, if the speed is greater than the Nyquist velocity, like this 32-knot radial velocity, the speed is read as minus 28 knots. We say the velocity has been folded. Does 30 knots seem like a low value for the low mode when the low mode goes up to 9 kilometers, or about 30,000 feet? Remember that the limit is on the radial velocity, and since the profiler beams are only 16 degrees off the vertical, the radial velocity component is only about a fourth of the horizontal wind speed. This follows because the sine of 16 degrees is 0.28. It takes a horizontal wind of 108 knots, blowing exactly in the direction of the off-vertical beam to create folding. For example, if the off-vertical beams point east, a 108-knot wind from the east or west will create a fold. But if the wind is 45 degrees off the east-west line, it would take a speed of 153 knots to cause velocity folding. The picture can be complicated by the presence of raindrops having substantial fall speeds, say a few meters per second. The manual gives an example in section 3.6, in which large raindrops greatly reduce the wind speed necessary to cause a fold. Like precipitation contamination, the folding of radial velocities will create wild horizontal wind errors, so conspicuous that they should be spotted easily by the quality control processing and by the forecaster. In fact, an unfolding algorithm may be implemented on the hub computer, where all profiler data are examined. Such unfolding routines have been successful with PPI Doppler radar data. Algorithms on the profiler hub automatically average the 6-minute radial velocity samples and then check the hourly average data for consistency. Like any automated procedure, the quality control algorithms may have difficulty in certain situations. If you know how the algorithm thinks, then you will understand when it will work best and when to be alert for possible failures. Here is the sequence of steps the data pass through. As discussed in the first training manual, the raw 6-minute radial velocity samples are combined to form hourly averages. This process is known as consensus averaging. In consensus averaging, only those data which mutually agree within a specified tolerance are accepted in the average. The tolerance is 1.5 meters per second for the vertical beam and 2 or 3 meters per second for the off-vertical beams. 2 meters per second when the profiler operates in low mode, and 3 meters per second in high mode. Here's how it works. This is a sample data set, 10 6-minute samples collected during an hour. Here the data are plotted on a line. It is clear that 7 of the samples agree closely. They are easily within a window 3 meters per second wide, centered near 3.5 meters per second. The other 3 samples lie within 2 other windows of the same width. These 3 samples are outliers. The consensus average of the 7 samples is 3.7 meters per second, while the average of the entire group of samples is 6.2 meters per second. Anyone would agree that the consensus average more accurately describes the measurements. Thus, this method is very effective at eliminating short-lived spurious signals like an airplane flying through the beam or moving ground targets. Whenever the signals are truly random in character, no consensus is found. In this case, it is highly unlikely that a group within a given window will have more than 3 members. A consensus average must have at least 4 members. In this case, the average is reported missing. The exception is in the processing of the vertical beam. If no consensus is found there, the average is reported as 0. Once the samples are consensus averaged, the hourly data are compared to data from previous hours and other heights at the same hour. Take a look at this portion of a time-height cross-section. It is customary to depict time increasing to the left, and of course height increasing as you go up. Here, the hour to be checked, the latest hour, appears at the extreme left. The first check is to compare the datum in question to the median of surrounding points. Here is the collection of observations. Unfortunately, we do not have data for future hours, so the collection is not uniformly distributed around the datum we are checking. The median is computed for each of the horizontal wind components. Here are the observed U components. Recall that the median is the middle value. Half the measured values are greater than the median, and half are less. Here are the U components again, lined up in order. For this collection of data, the median U component is 33 knots, while the observation being checked is 40 knots. We can't expect that the median and observed datum will agree exactly, so a difference threshold is specified. The threshold is a function of height and the wind speed, generally allowing more variation at greater heights and for stronger winds. A slightly greater threshold is allowed in the lowest few gates as well. If the difference for either component exceeds the threshold, the median is recomputed using data from just the current and previous hour. Maybe a significant wind shift occurred during the past few hours. If the difference from the median still exceeds the threshold, the observation, including both components, is flagged bad. Why do we use the median rather than an average? The median is not affected by a few outliers or extreme values, whereas an average can be adversely affected by a single outlier. Use of the median rather than the average thus prevents unchecked bad data from causing rejection of good data. For the case illustrated here, the outlier causes the average of the U components to be 14 knots, while the median, 33 knots, is still representative of the group. The median check filters the outliers and thus provides a rough edit of the data before the shear check. Because a bad flag set by the median check cannot be overruled in subsequent checks, the thresholds are rather loose. Bad data can pass the median check. The next step in the quality control system is the vertical shear check. In the shear check, the data are examined for consistency in the vertical only. No data from past times are used. Here is a sample of winds that might be considered in the shear check. The shear check steps up through the hourly profile, checking the vector shear between adjacent gates. A reasonable shear threshold is specified. It varies with height, wind speed, and the change in wind direction from one gate to the next. Greater speed shear is allowed when there is little or no change in wind direction in the layer, typical of jet core regions. Should the magnitude of the vector shear exceed the threshold, as in this example where the magnitudes are 20 and 35 knots, the shear is examined in greater detail. The shears in both layers are large and in nearly the opposite directions. This casts suspicion on the middle wind, which is 190 degrees at 20 knots. This wind is flagged. Next, consider the more difficult situation when two southerly winds at 20 knots lie between stronger southwesterly winds. The two middle winds agree with each other, but not with winds above and below. Here, adjacent shears are not both large, nor are they nearly opposite in direction. To allow for the possibility that both middle winds are bad, the U and V wind components are plotted on a graph, and a straight line is drawn between data in gates 1 and 4. If the components in the middle gates are reasonably close to the straight line, the winds are accepted. In this case, however, the middle two U components lie far from the straight line. Thus, the middle two winds are flagged. What if there is a layer of legitimately strong shear in the profile, as might be associated with a frontal zone? Consider this example. Since all three shears are large, further checking is required. As before, the U and V components are plotted on a graph, and a straight line is drawn through the data in gates 1 and 4. U and V components for gates 2 and 3 are considerably closer to the line than in the previous example. The winds in gates 2 and 3 would be retained in this case. How effective are the median and vertical shear checks when the data are really noisy? Here is a rare example from the Denver profiler at Stapleton Airport. It is easy to spot many bad data. After quality control, almost all bad data have been removed. Lest you get the impression that profiler data are error-prone, a month-long subjective examination of data from the experimental network in Colorado concluded that 96% of all wind observations were good. The reliability of data from the demonstration network in the central U.S. is expected to be still better. The human mind is very adept at pattern recognition, so far at least, much better than a computer. Unfortunately, quality control involves a great deal of pattern recognition and decision-making. Is the wind shift plausible? Does it fit a pattern common to upper-level troughs or fronts? Does it agree with the current synoptic and mesoscale patterns? The decision-making built into the quality control considers a small group of neighboring profiler wind observations. It doesn't see the big picture. For example, it doesn't look for a wind shift near the surface when a jet streak passes at 250 millibars. It does not consider outside information from Raywin sondes, satellites, or aircraft reports. For any given hour, it does not have the benefit of data from the next hour. Time continuity is one-sided. These handicaps of the quality control make your critical eye and knowledge of the weather situation the final judges of the data. Let's examine a case where this last line of defense is needed. In this case, a series of winds having very low speeds is reported at the 12-kilometer level. The quality control discarded the data in the early hours, when the erroneous data were fairly sparse. However, at these times, the erroneous data were highly correlated and comprised a large portion of the time-height cross-section. Thus, they corroborated each other in the quality control algorithm. How can we be sure that these data are indeed false? The 250 millibar charts for morning and evening show a weak jet passing to the north of the profiler's site. Based on this information, we conclude that wind speed should be 40 knots in the suspect area. Indeed, some of the profiler winds near the suspect area had a wind speed of about 35 knots. Remember this: in areas of weak signal, it is common to have low wind speeds. You should now have some insight into what artifacts can enter the data and what steps are being taken to eliminate them. The quality of the original data and the effectiveness of quality control routines should improve as more experience is gained with the demonstration network profilers. The quality of the output data, already quite high, should rival that of Raywindsonde observations. I hope that you will always view profiler data and any other data with a critical eye. You should now have a better appreciation of when the automatic quality control works well and when it doesn't. You are the final arbiter. Be sure to check the accompanying manual, number 2, for details not covered here.